recap some stuff because I'm really not remembering it.
All right, so there's been a request that we recap everything up till now.
Not like that.
All right, so let's do a quick recap here. So let's quiet down. We are in week 11 now, counting week 10 as spring break. We have all of our normal things going on. We have new assignments that are started right now, or will start at 11:30, I guess. Due next Monday. We got SI, UTF, everything going on. All right, we're into chemistry. Well, we're really deeply into the chemistry now of carbonyl groups. All right, we started out looking at carboxylic acids, and then we looked at reactions of really all the different carbonyl groups with strong nucleophiles. Now we've kind of separated out aldehydes and ketones, and we're looking at reactions of aldehydes and ketones with some weaker nucleophiles. Okay, we started out last time, the first nucleophile that we looked at was cyanide. All right, and that follows just a normal pathway. Cyanide's a nucleophile. To a tetrahedral intermediate, we protonate the alkoxide, so we get what was called a cyanohydrin. So there's a carbon with a cyanide or a nitrile group and an OH group attached to the same carbon. All right. We then started into what we would get if we reacted aldehydes or ketones with some nitrogen nucleophiles. Particularly, so far we looked just at primary amines. All right, when we react a primary amine with an aldehyde and ketone, I'll show up that overflowing slide that I drew out on Friday. If we react this with, let's just pick an aldehyde. What essentially happens is that we lose the oxygen of the aldehyde. It combines with the two hydrogens on the nitrogen to form a water molecule, right? And the nitrogen becomes attached right where the oxygen was. Okay, so we could just do this. We're going to have, here's our aldehyde. The double bond that used to go to the oxygen now goes to the nitrogen. Let's put a little R prime here to distinguish which one is which, and then we have loss of water. Okay? This functional group, anybody remember what this functional group is? Carbon-nitrogen double bond. It's called an imine. And we kind of briefly talked about, and there's really a more in-depth write-up in the text about how imines can be used to connect some smaller organic molecule into a protein. From aldehyde to an amine that's in the protein. The specific example we talked about was connecting retinal, okay, which is a visual pigment in the rods of the eyes. It's used for detecting black and white vision. Okay? And that retinal connects to a protein called opsin through a Schiff base. Well, this is sometimes called a Schiff base in biochemistry, but it's an imine. Biochemists make other names for things sometimes. And the trigger that tells the body or the eye or the nervous system that light has been absorbed is just an isomerization from cis to trans in the retinal molecule. Okay, so these are important in biology. All right, so what we're going to do today, I'm going to show you that mechanism real quick, but we're not going to spend a lot of time on it. And then we're going to look at a very similar reaction between an aldehyde or ketone, and a secondary amine. Okay, most of the process or the mechanism will be just the same, but it'll be different at the end because if we look at this secondary amine, there's two alkyl groups attached to this nitrogen. We imagine what we did here, we'd have two R groups to this nitrogen. Nitrogen with 4 bonds has a plus charge, so we have to it isomerizes in a different way to give us a neutral product. Okay, so there's just one difference at the very end. All right, once we've done that, we're going to look at some oxygen nucleophiles. We'll look first just at water, and then we'll look at the reaction of alcohols with aldehydes and ketones. Okay? So all of these reactions, the mechanisms are kind of lengthy, but what you want to do, instead of just looking at the whole thing and going, oh God, I'll never be able to remember that whole thing, you want to break it down into pieces, like we tried last time. And here, let's just take a look at it. I didn't make a clicker for on this stuff to see what you remembered. All right, so look at this thing. If you weren't here on Friday, see what you missed out on. All right, the other thing you missed out on if you weren't here on Friday was my lightsaber, I think. All right, so here's the way it works. So the nitrogen attacks the carbonyl carbon just like every other nucleophile reaction we've seen with an aldehyde. And we get this tetrahedral intermediate that's this zwitterion, meaning it's got a minus and a plus in the same molecule. The next 3 steps in the mechanism, all they are just acid-base chemistry. Okay? Because if we look at the product up here, and what we just talked about is we want to get rid of the oxygen. So the way to get rid of the oxygen is to protonate it twice to make a water molecule, which is then a good leaving group. Okay, so that's what we have to accomplish. We want to keep the nitrogen, so we want to deprotonate it. We want to get rid of the oxygen, so we want to protonate it. Okay? So we go through a couple of steps. We protonate the oxygen. We deprotonate the nitrogen. We can use the amine itself. I just put an R group on it as the base. Protonate the oxygen again to form a water molecule over here, right? And then that water molecule can come off. The carbocation intermediate that would be right here that would form is stabilized by the non-bonding electrons on the nitrogen, so we can draw a resonance. Excuse me. I'm going to get rid of the... So we can form this resonance here. We see we have the carbon-nitrogen double bond now, and then we just deprotonate the nitrogen, and we get the imine. All right? Yeah?
So can you explain to us again why the amine deprotonates the nitrogen group on the second step after the zwitterion?
Okay, so the question is, at this stage here, right, why does this amine deprotonate this ammonium ion? So each one of these steps is essentially just an equilibrium. All right, and we can think of an ammonium ion like this as being the conjugate acid for an amine. All right, so we have the amine here, which is more basic, and we have a conjugate acid, and so we just get a proton transfer, right? But at each one of these stages, the reaction can go forward or backwards. All right, if we get to here, if, say, this amine, if it deprotonated the oxygen instead of the nitrogen, but this oxygen, OH, is going to be less acidic than the ammonium ion, then it would go back. If it deprotonates on the amine, it goes forward. Okay? And so we essentially have a bunch of reactions here, and we'll talk about in a little bit for a whole series of these what we could do to drive the equilibrium one direction or the other. Okay? All right, so what happens if we have a secondary amine? Okay, so if we do the same thing, well, let's see. If we do the same thing we did before, let's just draw what? If we just replace the oxygen with the nitrogen, right? We'd have the nitrogen here, like this, and we would have a plus on the nitrogen. Okay, and really if we wanted to balance this, what we would also have at this stage, but we don't really form it because we're an acid, but we'd balance it, we'd have an OH, right? And so what's going to happen is from here we want to get to a neutral species. When we had the primary amine, we just deprotonated the nitrogen because we had the extra proton on the nitrogen, but we don't have a proton on the nitrogen here. So what we do, or what it does, is it loses a proton on the adjacent carbon. Okay, so we could just use the amine here again as our base. And what it's going to do is pull off one of these protons, and these electrons are going to go up like this, and the electrons can go onto the nitrogen. Okay, so in this way, we move those electrons up onto the nitrogen, we get a non-bonding pair of electrons on the nitrogen, and so the nitrogen will now become neutral. So, product that we get has a double bond down here now, and we have a non-bonding electrons here. Okay? So this species has a double bond, right? So what do we use for an ending for a double bond? Ene, right? And we have an amine, so this is called an enamine. All right? So when we react a ketone or an aldehyde with a secondary amine, we get an enamine. All right, so let's look at how this, one more time, how this takes place. So the non-bonding electrons attack the carbonyl carbon. All right, so then we get our first tetrahedral intermediate. Like this, and an H on there. All right, so now we have to do the same thing we did before. We need to get rid of the oxygen, so we need to protonate it. We want to keep the nitrogen, so we want to deprotonate it. And so we have a couple of different acid-base steps. So we're just going to use our trace acid here first. Protonate the oxygen. And we get to our second tetrahedral intermediate. All right. So now the next most acidic group here, well, we did that back, or the most acidic group here is the ammonium ion. So then we're going to use our amine again. It's the strongest base. Oops. And this is going to remove this proton here, and we're going to get our neutral tetrahedral intermediate. Okay, it's our third tetrahedral intermediate, because all we're doing is just acid-base chemistry, and I know we're all experts at acid-base chemistry, right? All right, so now we want to get rid of the OH. So what do we do so we can get rid of it? We protonate it, right? Because we need to make that OH into a better leaving group. This is the same thing we did back when we were studying alcohols last semester. All right, so then we can use an H+. Protonate and form a water molecule. A lot of things to keep track of here. That wasn't supposed to be an extra bond or anything there. All right, so now we're ready to get rid of the water molecule. All right, so the water can come off. It would form a carbocation at the position where the water came off, but that carbocation can be stabilized by the electrons on the nitrogen. All right, remember the most stable resonance structure is going to be the one that has complete octets for the carbons and nitrogens and oxygens and such. So these electrons can come down like this. And if we do that, that gives us this first intermediate that I drew up. Okay, so it goes from here, we form the double bond between the carbon and the nitrogen, get rid of the water, and we form that compound there. All right, and then we deprotonate. We call that the alpha position, the position next to the imine, or kind of the imine structure. Isomerizes to form our enamine. Yeah?
I'm curious about the neutral species where we have an amine and an alcohol group.
Mm-hmm.
Could we stop there? It looks like it could be a pretty stable product.
All right, so the question is about this neutral tetrahedral intermediate here. All right. These are some. Let me think about this. These species are, well, especially in a little bit of acid, are not going to be very stable because we can protonate on either side, making either the oxygen or the nitrogen into a better leaving group. Right? If we protonate on the nitrogen, then the ammonium ion will be the best leaving group, and it can go backwards. Right? If we protonate on the oxygen, then we form a water molecule, goes forwards and goes this way. Okay, so in fact, I think maybe if we were in a neutral solution or something, it would be more stable than if we're in acidic medium. Yeah.
Dr. Basin?
Yeah.
Just a quick question. So you just mentioned that protonated can always come back to the original one.
Mm-hmm.
So if we wanted to come back from this reaction, do we have to react it with like a base or?
Okay, so if we want to just go reverse the whole thing. Yeah, let's, the next slide is on that. I know, it's so hard to wait. Yeah, so the question is, and it's a good question, it's a good observation, is that because this whole process is in equilibrium, we can either go from, say, a ketone and a secondary amine to form this enamine, or we could go from the enamine back to the ketone and the secondary amines, right? So we can just push this reaction one direction or the other. We'll talk about on the next slide a little bit of what it takes to do that. All right, let's first just draw out what the product would be for this reaction down on the bottom. All right, see if you can draw that out. Okay, so remember, we could do this in 2 steps to make it easier, I think. The first step, if we have a secondary amine, is to remove the oxygen, right? We can just still draw the double bond, but remove the oxygen and attach the nitrogen. Okay, and I'm going to remove the hydrogen that was on the nitrogen as well. Okay, so here we've kind of replaced oxygen with the nitrogen, and we removed the proton that's on the nitrogen. Okay, so this isn't really the mechanism, right? But it's just kind of a formal way to figure this out. And then, what do we need to do in order to get to a neutral species? We need to deprotonate. Where are we going to deprotonate? Are we going to deprotonate over here? No, we're going to deprotonate at one of the alpha positions adjacent to the carbon of this kind of carbon-nitrogen double bond. Okay?
Good question.
Yeah.
So let's say there was like an alkyl group on one of those carbons. Would that, make one hydrogen?
Yeah, good question. So the question is, what if, let's just put one on there. Let's put a methyl group right there. Okay? So then we could get to here, right? And then we could have two possible enamines. Okay, so this could go like this. We lose a proton, and we can form either this enamine, or we could form this enamine. Okay, so the double bond we just have removed from this species here. We have to remove a proton to get the neutral species. We can either remove the proton that's adjacent to the methyl group to get to the top structure, or we can remove a proton on one of these other alpha positions to get to this bottom one. Okay? So if we look at those two structures, could we predict which of those structures would be more stable? The top one? Yeah. So why would the top one be more stable?
It has the most substituted.
Right, the most highly substituted alkene. So this one would be more stable. We get more of this product than we would at the bottom one. Okay, it's just using the same stuff that we learned before, right? So this one here would be more stable. And if this is all under equilibrium, and if we can drive it toward the product, then we would get more of the more highly substituted enamine. Okay? All right, so let's... Okay, so this is what we call a hydrolysis reaction. So lysis means to cleave. We're just going to use a water molecule to cleave this imine or this enamine. Okay? So see if you can figure out from, here's an imine, what products you would get. Okay, so all we're really going to do on this first one is we're just going to insert a water molecule in there, right? So we can just cut this bond right here. Let's just draw. Okay, we cut it. That's a double bond left. Here's the nitrogen, like this. Okay, we just severed those things. And we're going to use a water molecule to cleave it. Okay, so the oxygen of the water molecule ends up, here, let me do it in red, ends up here. Okay? And then the two hydrogens end up over here. Okay? Of course, if we're still in acid, what is it? Are these going to look just like those two products? No, if we were in acid, we would have added another proton to this amine. We'd have an ammonium. Okay? And if we wanted to get the free base, or this neutral amine, we'd have to add some hydroxide or something to deprotonate that to get back to the neutral species. We do all in the separatory funnel like we talked about before. All right, so what about the bottom one? Now that looks almost, that's exactly like the one I had on the last slide. That's too much of a giveaway. All right, so if we wanted to figure this out in 2 steps, what we could do is kind of isomerize this. We know if we protonated, here, let's do it in the reverse way. This would go down here, and we could pick up a proton on the alpha position. So then you get a nitrogen like this with a plus, and we picked up an extra proton over on the carbon. So once we've done this, then we just do the same thing we did up above. We cut this off. We're going to get the ketone, but we're only going to add 1 nitrogen on here. This. Okay, so like I mentioned, both of these reactions really should have arrows going in both directions. These are equilibrium reactions. All right, so the way that we can drive the reaction in one direction or the other is usually, you remember Le Chartrier's, however you pronounce that, principle from Gen Chem, right? So I'm going to take the water off of the middle here, and I'm going to put it over here. Okay, because it's one of our reactants. So if we had this imine, or if we just had this equilibrium, we wanted to drive it from the imine to the ketone and the amine, what could we do to drive it in that direction? Yeah, we add excess water. Right? If we have a whole bunch of water in this reaction, that means we have a lot of the reactant on this side. It's going to drive the reaction toward the products. Okay? So if we add here, add excess water, it's going to drive the reaction in this direction. Okay? What if we had the ketone and the amine and we wanted to form the imine? Well, the simplest point here would be to just maybe add an excess of this amine. Of the amine, and that would drive the equilibrium back the other way. Okay, I think I'll show you when we get to the reaction of the alcohols with ketones or aldehydes. Is another way to do that is not just to add an excess of a reactant, but if you can remove one of the products, then that works as well. And so another way, if you want to go from the amine and the ketone to the imine, is if you can remove water from the reaction, it will also drive the reaction in that direction. Okay? There's kind of a fancy little apparatus to do that. That's kind of ingenious, I think. All right? All right, so let's look at what happens when we add oxygen nucleophiles. All right? So we're going to start with just water as the nucleophile. Okay? And we can do this reaction, it's just a hydration reaction, right? We have a double bond, right? We did hydration reactions of alkenes. We add a H on one position and OH on another, right? We can do this hydration reaction under either acidic conditions or basic conditions, okay? So let's look at how it takes place. So let's say we add some acid. Okay, it could be a catalytic amount of acid. We only need a small amount because we're going to use it and then regenerate it. So where did I say if we have a ketone or an aldehyde, where is that functional group going to protonate? On which? On the oxygen, right? Because it has non-bonding electrons up here. I'm going to protonate up here. And we form this conjugate acid of our ketone or our aldehyde. All right? And this has an effect on the reactivity of the carbonyl carbon. What did I say? If we protonate, what does it do to the carbonyl carbon? It does. So it makes it more electrophilic because this can now more strongly pull electrons up onto the oxygen, and we get a larger contribution of this resonance structure. Okay, so by protonating on the oxygen, it increases the amount of delta plus on the carbonyl carbon, makes it more electrophilic. So now it's more electrophilic, and in fact it's electrophilic enough to react with a weak nucleophile like water. Okay? Otherwise, water won't react with it very well. Okay, so those are just resonance forms, so we can use either one of those to show our reaction. Okay? We can either show the water reacting with the carbocation resonance form, or we can show it reacting with the resonance form that looks more like the carbonyl. So then it would come into that, and then the electrons would go up on the oxygen. All right? So I'd use both of those red arrows on the left side. So when we do that, we end up with an OH here. And what do we have attached to this oxygen? Are we to the product already? No, because this still has both of the hydrogens on that oxygen. We have to remember that we used a water molecule as the nucleophile. Okay, so then what we're going to do is we're just going to deprotonate this and we're going to get to our product. Okay, so I'm just going to use a water molecule. Going to pull off this proton, and we form our hydrate, our product of the hydration reaction. Okay, so essentially what we've done is we've added an OH to one carbon and an H to the oxygen. So just like a hydration reaction with an alkene, we still OH one position, H at the other position. Okay? All right, so this is kind of, we could also call this a geminal diol. Geminal means both groups are on the same carbon. Gem diol. Okay, so the bottom one looks just the same, but this one we're going to use hydroxide instead. So we can use basic conditions. Now we have a much stronger nucleophile. All right, hydroxide is a much better nucleophile than water is. So we don't need to protonate the oxygen. Okay, hydroxide is strong enough on its own. So it's going to react directly with the carbonyl carbon. And then so we get O minus and OH. And then that can react with water. We just need to protonate it. And we get the same hydrate. Okay. So notice that when we compare the acidic conditions, so this is acidic up here, this is basic down here. We have similar types of steps in the mechanism, but we kind of reverse the process. So when we're in acidic conditions, we protonate first, and then our nucleophile attacks. If we have basic conditions, the nucleophile attacks, then we protonate. Okay, so it reverses those two steps. And one thing that's going to be important as we get into more of these kind of acid catalyzed reactions is that when we have it like up on the top with acid catalyzed, then we can only have either neutral species or protonated species, neutral or plus in acid. We'll never form a hydroxide or this alkoxide here if we're in acidic media. Okay, we just can't have hydroxide if it's in acid. Likewise, if we have it in hydroxide, then everything's either going to be neutral or a minus charge. Okay? So we have to be careful not to mix those conditions and make sure that we're consistent. Stable are these hydrates. All right, so it depends upon the aldehyde or the ketone. All right, and there's kind of two things that are going on here. One has to do with the stability of the actual carbonyl group, and one has to do more with the stability of the hydrate. All right, so the carbonyl itself, remember, has this delta plus and delta minus. So the more stable carbonyl is going to be the one that has kind of reduced the amount of delta plus on the carbonyl carbon. So if we have an electron donating group, remember we talked about before, if we have an ester or an amide, they have an oxygen or a nitrogen on the carbonyl, those are less reactive. Okay, it's because those groups can donate electrons. Here all we have is either a hydrogen or alkyl groups. Which is better at donating electrons, the alkyl groups or the hydrogens? The alkyl groups. Okay, goes back to stabilities of carbocations. Remember, if we have carbocations, the more alkyl groups we have attached, the more stabilized it is, right? Because they can donate electron density. Okay, so if we look at the carbonyls up across the top, we see that we're increasing the stability of the carbonyl group as we add alkyl groups. Okay, from formaldehyde to acetaldehyde to acetone. It's getting more stable going to the right. Okay? If we draw out the hydrates across the bottom, notice each of those have two OHs now attached. What do you think is going to affect the stability of those hydrates? Is there something to do with steric strain? Yeah, exactly. So it has to do with steric strain. So if we look at this hydrate from acetone, this has two methyl groups here. And we're going from sp2 hybridized, or trigonal planar up there in the carbonyl, so everything's kind of far apart, to a tetrahedral down here, so it's pushing those methyl groups closer to each other. All right, so this over here has more steric strain. Okay, so that makes it less stable, right? So for the hydrates, it gets more stable as we go to the formaldehyde side. For the carbonyl groups, it gets more stable as we go to the acetone side. Right? And hydrates, more stable to the left. For the carbonyls, more stable to the right. All right, so these are both kind of working together. And so here are the ratios here, right? If we have formaldehyde up here and we put it in water, we essentially get almost completely the hydrate. Okay, this is what an aqueous solution of formaldehyde is, what they call formalin. It's a, stabilizing, preserving solution. If we have acetaldehyde, we have almost 1-to-1, and we can't see it over here, but if we have acetone, it goes completely the opposite direction, only 0.2% of the hydrate. Okay? So these hydrates in general are not that useful to us. Okay? But the process is important with an alcohol. Okay? So I'm just going to draw out the products here, and then on Wednesday we're going to go into all the details here. Okay? So these are typically, well, always acid catalyzed. So we add a small amount of sulfuric acid or hydrochloric acid or something like that. Just like with alkenes, remember we could do a hydration. We could also add an alcohol where it adds H to the one side and the O alkyl group on the other side. Okay, so that's same thing's going to happen. Okay, so we're going to get our first product. It looks like this. Here, I'll put the new groups in red. OCH3 and H. Okay, so it's just like the hydration, right? Except instead of having the OH, we have OCH3. Okay? Now, this can react again, all right, if we have enough alcohol here. So we're going to put plus the alcohol again. And in the second step, what happens is that the OH gets replaced by the OCH3. Okay, so it's more like a substitution of this, kind of an addition first, and then a substitution. And so then, I guess we can just draw both of these. OCH3, we get another OCH3 over here. Like this, and we've lost a water molecule. Okay? The product here with two OCH3s is called an acetal. Okay. The one in the middle is kind of halfway to the acetal, or half acetal, and so we call this a hemi, means halfway or something. Hemi-acetal. Okay? So, if we think about how this is going to take place, it's going to be very similar to what we saw when we were doing the reaction with the amine, right? We have it in acid, it's going to protonate on the carbonyl, the alcohol can be the nucleophile. You're going to go to notice that the hemiacetal is essentially just a neutral tetrahedral intermediate. All right? And then we're going to see how we can replace that to go all the way to the acetal. Okay, so there's going to be quite a few steps here, but again, what we want to break down is to notice where we're just doing acid-base chemistry. We want to keep in mind what we're trying to accomplish, right? So we can kind of know where we're at in the whole process. Okay, so let's just stop there for today. I think that's enough for today. All right, I'll see you guys on Wednesday.